Hello, hello. I'm LAKSHAY, a second year BTech student from IIT Roorkee. My branch is Data Science and AI, and I'm going to discuss a topic: computational time complexity of PCA is a part of our course EA 201, applied linear algebra. First of all, what is computational time complexity? Time complexity of an algorithm quantifies the amount of time taken by a program to run as a function of length of the input. In simple words, it is a measure to compare two or more algorithms. One is better in terms of time taken by them to terminate or to solve a problem. Notation for time complexity is O of n, where n is the input size, or we can say it is the size of the problem. This is the worst case time complexity of the algorithm. What is worst case? For example, if we have to find a number from a list of numbers, then first case, that is the best case, is that if it is present at the first position of the list, then we just take one comparison to find its element. If our algorithm is to go through the whole list from starting to the end, it is the best case. But if that number is present at the last of the list of those numbers, then we have to go through the whole list, find that number, which takes the maximum amount of time to find that number to solve our problem, which is taking n minutes of time. So we denote it by O of n. So mathematical definition of O of n is given here. It is a definition. An algorithm takes f of n units of time first terminate, then we say that it has a time complexity of n, which implies that there exists a constant c1 and a constant n naught, such that f of n is less than c1 times g of n, or all n greater than n naught. Usually, we talk about the higher values of n, as in real world problems, we have large values of n. Okay. For example, if an algorithm takes at most n square plus n units of time to terminate, then its complexity should be, according to the definitions uh, as per we have seen till now, complexity should be of n square plus n. But as we know that for large values of n, for example, if we take n equal to 10 to the power 6, then n square would be greater than n, very much greater than n. So n will be not be significant as compared to n square. So we say that it has a time complexity of n square. So the of n square plus n and of n square, they both are the same. Because for large values of n that are the same. So we have a note. We usually take an assumption that addition, subtraction, multiplication, division, and these type of simple operations take only one unit of time. That is the smallest unit of time. Now, why are we studying this? Why are we talking about this computational time complexity of PCA? The problem is that we are so used to live in three dimensions that our intuition fails to imagine even 4D things. We cannot imagine, cannot visualize the things beyond 3D. For example, if we see in this figure, we are having a point which is zero dimensional, then we have a line, then we have a square, then we have a cube. We are able to visualize them with no problem. But as we move to fourth dimension, it is a 4D hypercube. It is very hard for us to visualize in our mind. Another example, for example, if we another problem that is due to this curse of dimensionality is that if we pick 2 points randomly in a unit square, the distance between those 2 points on average is approximately 0.52. We pick those If we pick two random points in 3D unit space, then average distance would be 0.66. But what about 2 points picked randomly in a million dimensional hypercube? The average distance comes out to be 408.25. The result of this is that our high dimensional data sets become very sparse. Most of the training instances are likely to be far away from each other. because there is too much distance between them. So in a huge space, the points are very less. It also means that if a new instance comes, it will likely be very far away from training instance. So, which means that it is very much difficult for us to make good predictions as compared to lower dimensions. In lower dimensions, we could we have less space. Also, the distance is less, so we can have good predictions. But if we are in high dimensions, then the distance is also increased between any two training instances on average. So it is very difficult to us to give reliable predictions as they will be based on too much extrapolation. So in short, the more the dimensions the training set has, the greater the risk is of the overfitting it. So we got two problems because of the curse of dimensionality. The solution to the second problem, we can think of that if we have too much space, we have less data points, we can increase the number of data points. That's no problem. Here we took 2 points that were on the bound near the boundary. That was the condition. That we are taking points that are near the wall up to a distance of zero point 0.1 units. So one of the solutions is that we can increase the size of the training set to reach a sufficient density of training instances. But if we do so, the number of dimensions increase exponentially. Suppose if we are fitting a curve, we are in higher dimension. If we increase the number of points, then dimensions will increase further. Okay, that is a problem for us. Uh, we have Suppose if we have 100 features, all are ranging from 0 to 1. So we will need more training instances than the atoms in the observable universe in order for training instances to be within zero point 0.1 of each other on average. That is a very huge number. So it is not applicable in practice that we can increase the training set, the size of the training set. So what we need to do is dimensionality reduction. Here comes the need of dimensionality reduction. And the most popular technique for dimensionality reduction is PCA, full component analysis. Let's go through it. What is PCA, principal component analysis? But to, if I explain it in simple words, identifies a hyperplane that lies closest to the data, then it projects the data onto it. For example, we have here an image. We have a 3D data set with red and blue points. With the red points is in 3D, and we have this hyperplane. We have this hyperplane, this blue one, and we projected all the red points onto it, and they will become blue points. So the 3D data set is projected on the 2D subspace. In this way, we reduce the dimensions of our data, right? So it is the it is what PCA does. Let's go now. We are we have to find out its computational time complexity. Let's let's compute its complexity step by step. Let's start. First of all, we are assuming that we have m number of instances and n number of features, and we have to find mean of each feature. First step is find mean of each feature and subtract mean from each instance. Okay, we have a code for it. Let me run this and I'll tell you how to do. Here we have. First of all, I took a random data set that is which has numbers from 10 to 50. From the range is 10 to 50, and there are 100 data points, and the shape of the data set is 20 comma 5, which is 20 rows and 5 columns. Means there are 5 features and there are 20 instances. The value of m is 20 and value of n is 5. Our data looks something like this. The data. So first of all, what we did is that we entered the mean. First, we find the mean. Is the mean for data, and what we are doing, we track the mean from each instance. It is our data. It is the mean from each instance. The mean is being subtracted. So now our data is mean centered. So our new data will be something like this. We find mean of this data again, then it will come out to be 0. So our mean shifted to origin, and our whole data set is mean centered. Okay. The first step is done. Now, what were the steps involved here? First of all, what we were supposed to do is that we have to find the mean of the data. To find the mean of the data, what we do is uh, add all the instances and divide it by the number of instances. So we have m instances for each feature, and there are n features. Time taken for this number of operations are m into n, and then we have to subtract those mean from each instance. It will also take m time n subtraction operations. So total there are mn subtractions and mn additions, and some lower number of divisions also, that are divisions by the number of instances. So highest number of operations are of order of m of n. We say that this first step took the time O of mn. Okay, for finding one feature, for finding mean of one feature, it took O of m time, and we have n features, so the complexity of this step is O of m. Then what we do is that we compute the covariance matrix of the features. So where here we have two functions. Let me explain them. In Okay, if we are given two vectors x and y, any two features if we have, it will return the covariance of the two vectors. Just it is finding the mean of those two features, and then is doing is as per the formula that we know mathematically, x minus x mean into y minus y mean. Sum of these, all of these divided by the length of uh, the number of instances that we have minus 1. It is the formula for covariance. It is a function for covariance of two vectors x and y. Then we have covariance matrix. Um, First, we have here we will store our covariance matrix here. Then first we have a loop that is running um, number of times as are the number of features. X dot shape would be 20 cross 5. As here is minus 1, it will take the last dimension, that is 5. So I is in range of 5. Okay. Now for each row, covariance matrix will have 5 cross 5 dimension. So first we are finding first row, then second row, and then third row, then we are appending it here. Okay. Now for finding each row, what we need to do is that first row will have the covariance of first element with the first element. Then second element will be uh, covariance of first feature with the second feature. Then first feature with third feature, and so on. So in the covariance, in the covariance matrix, in the row covariance, we are appending feature wise. First of all, it will be 1 comma 1, then 2 comma 2, 1 comma 1, then 1 comma 2, 1 comma 3. It will be stored in first row. Then it will get appended to this matrix. Then will this loop will end, and it gets appended to here. Then it will again run. I will become incremented by 1. Then we will have again empty row covariance. Then we will start appending pairwise features covariance, and again next row will be appended to this matrix. Okay, so we at last we will have a 5 cross 5 matrix. Or let me show you the code. This comes out to be our matrix. This is our first row. This is our second row. These are our 5 rows. Okay, so we have found the covariance matrix for our mean centered data. For talking about its time complexity, for finding covariance matrix, we executed this function covariance matrix at once. We need to find the time taken by this function to terminate, to complete. So first of all, here we can see we have this one loop and then second loop. In this loop, here we have nothing. It is only of it takes constant time to create a new row. This is getting a empty list. It is of constant time. It takes constant time. We are just allocating a memory to a list. Okay. Then in the second loop, it is our second loop. Here we are finding covariance of the elements. So for as we can see that I for this loop, for only this loop, I is fixed. So we know that it is number of features. So it will find the covariance of ith element, ith feature, and the jth feature. It will append it to row covariance list. So this loop, for one iteration of this loop is being executed n number of times. That is the number of features. And this is also being executed n number of times. Total it is n square. But here it is we have a function covariance of these two. So we will need to have so we need to come to this function. What amount of time it takes to compute this? We have two vectors. First, we have to find the mean. Mean will take m units of time because there are m instances. M units of time for this, m units of time for this, and it will just take constant time. No, it will also take m units of time as they are being added. And dot sum we have. So total, this whole function is taking m units of time. So O of m. Now we can see this loop is being executed n number of times. That is the number of features, and this function takes m units of time. So this whole loop takes a time mn, m into n. Time is being taken by this loop to finish for one time. And this loop is also being called or being executed n number of times. So mn times this loop and n times this. So total it becomes mn into n, which is m square m into n square. The total amount of so the time complexity for finding covariance matrix comes out to be of mn square. Okay. Oh, sorry. There's a mistake in this slide. I will correct it afterward. Now, as we have found the covariance matrix, now our next step is to find the eigenvectors of that matrix corresponding to the eigenvalues in the decreasing order of eigenvalues. So for finding these eigenvectors and eigenvalues, we will use power method. Okay. So we have a code for this. We have already found covariance matrix. Now what we will do is that we have this method, this code for the power method. Okay. We have set tolerance that I will tell when we come to have a use of it. Okay. I have created a list for eigenvalues and a list for eigenvectors to store them First, we have a loop that will that corresponds to each eigenvector and eigenvalue pair. Okay. Now, what I'm going to do is basically in this loop, what I'll do is that here I find the new eigenvector. Here I find the eigenvalue. Now I check that if the previous eigenvalue and the eigenvalue that I found now, the difference between them is less than tolerance, then I'll stop and append it, append the eigenvectors correspondingly in the lists. If this condition is not applicable, then our loop will go on up to maximum iterations. Okay. So in this way, one when this loop terminates, it's completely executed, then uh, I am with with a pair of values, one eigenvalue and eigenvector in the two lists. Okay. Then again the lambda previous is changed to zero, and again this is iterated. Now again the slope is executed. It is the initial guess again. Then in the same way, eigenvalues and eigenvectors are being found. It is the condition. It is the update rule for the matrix. When we apply this, we are able to find the next highest eigenvalue that that is smaller than the one that we found in previous step. Here we found the next highest eigenvalue and the corresponding eigenvector also. So in this way, using power method, I find I find the eigenvector and eigenvalues of the covariance matrix. Now we will see the complexity of, okay, as we can see that this loop will be executed n number of times, that is the number of features. This loop is there which will take maximum 100 times, that will execute maximum 100 times. Okay. Now it is x is being calculated, and it is the eigenvalue. It is the eigenvector. As we can see, as per the dimensions of these matrices and vectors, this whole loop, if it is executed one time, it will take n cube time to execute, n square, sorry. It will take n square time to execute. And if this loop is, and corresponding to this loop, this will be executed, this uh, will be executed n times again, the same processes. So overall, this whole loop will take time n square times n, that is n cube. The complexity of this for finding eigenvectors and eigenvalues is of n cube. So here we have found the eigenvalues, and here we have eigenvectors. Now we choose the dimensions, the number of dimensions that we want to reduce it to, and then we just take a dot product of these two, which will take time of, then we'll see in next step. It is our next step. Okay, so this operation for finding one eigenvector, we saw that took of n square, and for n eigenvectors it will take of n cube. Now in the next step, when we take dot product of the data points, these are data and these are eigenvectors, we choose the dimensions that we want to reduce it to, and we just take a dot product of them. This will take a time complexity. This dot product will be of mn, and then we have the complexity of all the four steps. Now we have to just add them. When we multiplied this, we found the this is our data, which was earlier like this. Now it was 20 cross 5 dimension. Now here the dimension is is reduced to 20 cross 3. This is how PCA works. Now the overall complexity we have to calculate, as we have the complexity of all the four steps. Now first step took O of mn time, then next step took of m square n time, next n cube, and next was mn. Now we can see that mn is obviously less than m square n, or we can see by degree. Okay, degree of this is 2 mn, 1 plus 1 2. Here the degree is 2 plus 1 3, here it is 3, here again it is 1. So highest degree terms are this and this. These two terms are of the highest degree, so we just take them and leave other ones. So the overall complexity of our algorithm, that is PCA, is of m square n plus n cube. Thank you for bearing with me. Bye. Thank you.